Assalamu alaikum warahmatullahi wabarakatuh. Today we will be starting the signal conditioning. So after when you have to use a sensor, you may have to do several signal conditioning phase before you can process the signal. So once you do the signal conditioning, which includes, for example, amplification, conversion from mechanical signal into electrical signal, filtering of the signal, manipulation, and protection. Once you do all these things, then when you will go to the next phase, which is signal processing. So let's see how we can carry out various signal conditioning through amplification, conversion to electrical signal, filtering, manipulation, and protection. We will be discussing some of the mathematical problems examples here as well, inshallah. Okay, for amplification, we always use, most of the time is we use the op-amp circuit. So, and a basic op-amp circuit looks like this. So this is an op-amp chip. So you have basically inside got many transistor and other components. So, but the schematic of an op-amp looks like this. So you will have a triangle with an inverting input and a non-inverting input, and you will have various other outputs and inputs as well. So this is a typical op-amp chip, LM741. So let's go through some of the um, conventional op-amp circuit that we will be using for various purposes. So in mechatronics or industrial automation, you will be using this type of amplifiers, such as inverting amplifier, non-inverting amplifier, differential, summer amplifier, and voltage follower. So inverting amplifier would look like this. So so this is the inverting amplifier. Why it is called inverting amplifier? The gain is negative because your input is connected to the negative of the, as you can see, the negative of this negative input of the op-amp, and the ground is connected to the ground. Sorry, the non-inverting input connected to the ground. So this is the basically the gain. How to derive this gain? So you have to understand there are two things. Is that there is no input current to here. This is 0 ampere current into the op-amp, and this voltage, these are virtually same thing. They are same. So V1 equals to V2 equals to 0 because V2 is connected to the ground. So this is an approximation. We can assume this. Now, if we can do these things, so then we can easily carry out the circuit analysis. So the current is flowing through this to this direction. So basically you will have the current flows through this is equals to V in minus V out divided by RF plus R. So also you can think the same current is also flowing in this loop because this is virtually grounded. So you can say that I equals to also equals to V in over R. So if you come up with these two equations, so you will have basically V in by R is equals to V in minus V out over RF plus R, which will eventually will give you uh, V out by V in is equals to minus RF by R. So this is the non-inverting amplifier gain. So this is we call the gain. The how much is the gain? So if you have higher value of RF, let's say 100, and R is 10, so you have 10 times gain from your input voltage. So this is a non-inverting amplifier, inverting amplification because the sign has been changed. So now let's see non-inverting. In the case of non-inverting, you have the voltage connected to your positive terminal of the op-amp, and this is the case. And if you see from here, basically, you can think this as a voltage divider circuit, this whole thing as a voltage divider circuit until here. And let me redraw it. This is the voltage divider circuit you can consider because this is same voltage and this is the input coming in directly here. So this is how it is connected to the ground. So you can say the voltage divider circuit to be, let's say you have voltage here V1. So V1 is equals to V out times R over R plus RF. All right. But we know that this V1 is same as V in because they are virtually the same thing. So we can say also V in is equals to V out by R times R by R plus RF. So V out by V in would be equals to 1 plus RF by R. Sorry, 1 plus RF by R. So this is the case for non-inverting amplifier. So the difference is basically you have always the gain is higher than 1, at least it will be higher than 1 or equals to 1, and basically you will have positive, same as the voltage sign will not be changing from input. So this is the case. Let's pause here for a while, then we come back again. Okay, let's move on to the next slide. So sometimes we may have something called a voltage follower. So in this voltage follower, it is exactly same as a non-inverting amplifier, except there is no resistance network here. So if there is no resistance network, we have the formula for non-inverting amplifier is V out equals to V in times 1 plus RF by R, where if we put RF, because it is short circuit now, so RF can be equals to 0. So in that case, V out will be equals to V in. So this is a simple voltage follower circuit. Now, why do we need a voltage that is exactly same as input voltage? What is the purpose of having an op-amp circuit in between? The reason is op-amp has a characteristics of high input impedance, so it will not draw any current and it will have less loading effect. Let's say you want to you develop a voltmeter, so you don't want to uh, have a condition where the voltmeter itself will draw current to measure the voltage across the system. So what you want to do, you want to minimize the current drawn by the voltmeter, and still you would like to measure the voltage across the circuit. So for this case, you would like to have a device that will have least loading effect to draw current by itself. Just parallelly, it will measure the voltage. So this is an example. So these type of cases, you may want to use a voltage follower type of circuit, which will have high input impedance. Okay, Similarly, you have here differential amplifier. In this case, basically you are getting the difference between two voltage input, and this is the case. So this, if you recall back the encoder circuit, incremental encoder, we have mentioned that you can use an op-amp circuit to subtract these two values so that A and A bar, so the noise can be eliminated. So similarly, you can have a sensory network that we would like to have the addition of different sensor values. So this will have the addition or summing amplifier. So this is called summing amplifier, and the other one is called differential amplifier. Okay, now let's come to the impedance. Impedance is a very important concept of any electrical circuit. So let's try to explain the impedance with a drawing, then you will understand. So let's say you have a voltage source. So we have both input and output. So we will discuss it here. So let's say you have a voltage source here at Vs, and then you have a black box circuit connected here, which is having a load of ZL. So this is can be say that before it goes into the load, so it can be somewhat equivalent to this, like Vs, and it will have some internal resistance. Every voltage source has some internal resistance, and then you will have a input impedance of this whole system, Z in, and then you will connect it to the load, which is ZL. So you would like to have the full voltage coming across to this Vs prime. So you want Vs prime to be as close as possible to Vs. So let's say if you have a Vs prime calculation. So Vs prime is from this, because this is a voltage divider circuit. So you will have Vs times Z in, input impedance, divided by Z in plus Rs. Now let's say if your Z in is very high value compared to Rs, so you can just ignore Rs. So basically, if you ignore Rs, then you can eventually ending up getting Vs prime is equals to Vs. So this is what we want actually. So this is what we want actually. So in this case, basically your full voltage you are bringing in to the system, to the actual load, to across the load. If your input impedance is low, so you having an input impedance to the system. The system has an input impedance of low value, sorry, not low value, high value, so that you can have a full voltage representation across the load. Input impedance should be high. Now let's talk about the output impedance in the same manner. So in the case of output impedance, when you want to attach uh, the device to this to something, so you have also output impedance. So output impedance, on the other hand, let me erase this thing first. Um, so let's say you have a voltage Vs, and then you have something connected here, and it has a load of ZL. Now let's say this can be having an equivalence of like this. So you have, let's rename it not VS, rather VO, just to differentiate between the previous example, VO. So now this VO, this one will have some, when you are connecting the load, it will have some output impedance. So you have basically ZO, and then you come here, ZL. So in the same manner, if you want, so basically your VO prime here, you want to have the full voltage across the load. So VO prime is equals to uh, VOZL by Z0 plus ZL. Now again, if your Z0 is very small compared to ZL, the load resistance, then you can ignore the ZO, means the output impedance, and then you can have VO prime is equals to VO. So in both cases, you want to have this ZL to be as high as possible compared to ZO, or ZO to be as low as possible compared to the ZL. So your output impedance should be as low as possible, very minute in scale, and input impedance should be very high so that you get the full voltage representation across the load. So this is the key factor you have to remember. Okay, let's move forward. Okay, now sometimes just one op-amp may not have enough low input impedance, high input impedance, and high common mode noise rejection ratio. So that's why sometimes we go for instrumentational amplifier, which can significantly increase the input impedance to very high value, and so on and so forth. So this is called instrumentation and amplifier. So it is a complicated op-amp circuit with three op-amps connected together. So we are not going to discuss this analysis of this circuit. However, this is used as compared to pure one op-amp circuit. Okay. So signal conversion is another technique that thermistor resistance is in temperature measurement. So it's basically changing the resistance. Sorry, I have to pick up this call. So we pause here for a while. So the thing that I was discussing, that you have to convert the signal into a reasonable electrical equivalent, like either voltage or current, so that we can measure it using electronic circuits. So thermistor changes the temperature, so you have to attach it with a voltage divider circuit or a kind of what do you call this Wheatstone bridge circuit to measure the change in the resistance as a proper voltage output. So for example, LDR also can be used for measuring the resistance change due to the change in the light intensity. So we can use these to measure the light amount of light present in a certain room. So let's say this is a voltage divider circuit where R2 is an LDR, light detecting resistor, whose resistance varies between 4 to 12 kilo ohm depending on the light level. if R1 is a 10 kilo ohm and Vs, meaning to say this voltage supply voltage is 5 volt, then find the maximum and minimum value of Vd. What is this Vd value? Which is V out, and the range of the output impedance, because this LDR changes the value, and the range of power dissipated by R2. So so this is for any voltage divider circuit, the Vd equals to R2 times Vs supply voltage divided by R1 plus R2. This is a very basic circuit. You can just use KVL, KCL to solve this circuit. So this, I'm not going to discuss that one. Okay. So the minimum Vd when R2 should be 4 kilo ohms. So this is Vd minimum, which is 1.43 volt. And when R2 equals to 12 kilo ohm, Vd maximum, which is 2.73 voltage. Now, input and output impedance, if we want to measure for a voltage divider circuit, so we have to see from here what is the input impedance. So from here, we can see from the source side that the input impedance is basically R1 plus R2. So Rin is basically R1 plus R2. But output impedance can be found by using Thevenin circuit model. So in Thevenin circuit model, your VTH equals to Thevenin voltage is equals to the same output voltage, and uh, basically RTH is, you have to shorten this source, shorten the output, and you can find out the ISS, short circuit current, Vs by R1. So this is your VAS, VTH, and this RTH, which is VTH by ISS, and your RTH would be equals to parallel combination of R1, R2. So basically, if you shorten these things, it will become a parallel combination of R1 and R2. This is your uh, output impedance of the voltage divider circuit. Now this output impedance is a variable because your R2 is varying. So if you vary R2 according to 4 kilo ohm to 12 kilo ohm, then your output impedance will also vary. So that calculation can be done. Okay. Now let's talk about a Wheatstone bridge circuit. So this is a typical Wheatstone bridge circuit. Usually you have these R1, R2, R3, R4 are the known resistor, and RG is your sensor that varies with respect to some parameter variation. It can be a strain gauge, it can be a LDR, or any sort of this sensor. So usually for convenience, what we do, so this is the solution for V1 minus V2. V1 and V2 is V1 minus V2 will give you the output voltage, which is this. Now for in designing bridge circuit, we only need to choose only 3 parameters. So basically what we do is, let me show you. Okay. We can ignore this one. Okay, what we do in Wheatstone bridge circuit, we try to maintain the condition balance where you will have this condition, then your V out minimum and V out minimum would be 0, which we call balance condition. And usually if you have RG, R2 and R3, R4 are same at balance condition, then you will have V out equals to del over 4 plus 2 del V in. Now del equals to the change of resistance. So del R by R. So this is your change of resistance, means the RG, how much it has been changed. So this change of resistance will give you this del, which is very small. So if it is small, so 2 del will be even smaller because it is 0.001. So it is a very small number. So we can assume that 2 del to be equals to almost equals to 0. So your V out can be simplified del over 4 into V in. So the power dissipation is given by this, which you have to ensure that maximum allowable power across the sensor is W max. So you should make sure that your power dissipation across this sensor is less than W max. So this is basically your Wheatstone bridge formulas that you need to remember. Okay. Now let's talk about a simple example. A strain gauge with a nominal resistance Rg equals to R. All other R2, R3, R4 equals to R, and Rg is equals to R 600 ohm is installed in a branch Wheatstone bridge circuit. Unstrained gauge is at unstrained gauge R1, R2, R3 equals to R equals to Vs equals to 10 volts. The strain gauge is subject to a strain, and the digital voltmeter gives you a 5 millivolt V out. So the V out equals to 5 millivolt. Calculate the resistance change. So that what is the del R, and calculate if the gauge factor is G equals to 2. Now we know that V out equals to del over 4 V in. So the V in equals to your V supply voltage, which is 10 volt. So your V out equals to 5 millivolts. So you can find out the value of del. So the del would be equals to, if you find out V in 10, 5, so del will give you 20 times 10 to the power minus 3 over 10, which is 2 into 10 to the power minus 3 volt. So now these 2 into 10 to the power minus 3, not volt, it is unitless. Now again, gauge factor equals is basically nothing but del over G equals to the strain. Strain is epsilon del L by del L. So this is how you can, this is the formula. And so your change in the resistance is del R, as you know, del R by R equals to small del. So this R, you know, is 600 ohms. So 600 times 2 into 10 to the power minus 3 is basically del R change in the resistance is 1.2 ohm, which is given here. And calculate the strain. So the strain equals to del over G. Del is 2 into the 10 to the power minus 3 divided by G equals to 2. So it's basically 10 to the power minus 3. This is 10 to the power minus 3 is the strain that you, this actual physical strain. So this is a simple example. These type of questions we will be asking in the exam. Okay. Now, sometimes we want to convert current to voltage. So as you can see, you have a current source, current going in. So V out equals to IR because the same current flows through this. So you will have V out equals to IR. Okay, next is the filtering. Now, this is very important. We will be discussing some mathematical problems in these filtering questions. So the filtering would be only passive filter. Passive filter means you're going to only use RLC circuit, mostly R and C. We are not going to use any active element like op amps as such. So we are going to use only RC circuit to design a filter. So the filter, what we want to do is basically, if you have a capacitor across the load, so basically you want to allow low frequency signal and high frequency signal, you can see the output voltage eventually goes down. So the high frequency signal cannot pass through this circuit. So the equation is given by this, V out by V in equals to 1 over 1 plus F by Fc whole square to the power root over to the power half. So F and Fc is called cutoff frequency. F is the frequency of interest. So design step is, first you have to find the critical frequency, and the critical frequency is given by the 1 over 2 pi Fc formula, and select any capacitor in microfarad to picofarad range, and then calculate R. So if R is too low or too high, require high current, so you need to do some trial and error. So let's say we want to design a low pass filter. A measurement signal for a sensor is in a range of less than 1 kilohertz frequency, but there is an unwanted noise at 1 megahertz. So design a low pass filter so that it attenuates this noise to 1%, meaning to say your V out by V in should be 0.01. V out by V in should be 0.01. So you know that V out by V in equals to 1 over root over 1 plus f by fc whole square. So your what, and you have to also check what would be the actual frequency at 1 kilohertz, which is your measurement frequency. What will happen to this? So V out by V in, 1% means 0.01. So your uh, F means frequency of interest, which is you would like to eliminate the 1 megahertz. So what is this 1 megahertz? So F equals to F2 equals to 1 megahertz. So if you key in all these values here, you will get FC to be 10 kilohertz. So your cutoff frequency is 10 kilohertz. So you can then find out what is the value and what is the value of 1 kilohertz. If you put 1 kilohertz here, you can still have 99.5% of only 0.5% attenuation. So you still have the good amount of signal, which is 0.995. So, and I have put it in the Excel, as you can see that 1 kilohertz you have still good amount of signal, 0.9995, and lower is even higher. And then it eventually attenuates, and at 1 megahertz it goes to only 1% signal. So this is the, so it fulfills my desired filter design. So once you have the FC, now you can calculate the required uh, resistance and capacitor value from the equation that I have shown you in the earlier slide. So this is the graph plot. So this is the FC equals 1 over 2 pi R is RC. So your capacitor should be 100 picofarad to megafarad, microfarad. So R will be 159.236 kilo ohm. You can do a trial and error to get a reasonable value of R that is easily available in the market. Okay, now let's talk about an high pass filter. The equation changes a bit. You have F over FC whole on the top, and here bottom is this thing. And FC is still remain the same, 1 over 2 pi RC. Now here your capacitor is in series. So you have this high pass filter. You are allowing the higher frequency to pass through the system. This is an ideal case. This is an actual case. Ideal case, you will have a step response, but in real case, you will have a S-curve response. Now, when you have a high-pass filter, another example is this. A measurement signal has a frequency that is higher than 500 kilohertz. So you want to measure a frequency higher than 500 kilohertz, and you have an unwanted noise at 1 kilohertz. Design a high-pass filter that will attenuate this 1 kilohertz to 1%. Mean to say you have 0.01 value of V out by V in. So again, do the same thing, find out the FC. Now your FC is 100 kilohertz, and then if you get the Excel sheet, you will see at 100 the noise 1 kilohertz, you have 0.01, but at actual signal you have considerable amount of signal, as you can see here. So this is the case. Similar to this is the plot. Okay. In the case of band pass filter, you have a basically high pass and low pass. You allow the high pass and low pass, and then you have the band. This is the band you have. So basically, and band stop means you want to stop some certain signal in this band. So now this is an example. Let me try to do it here. So you have a signal condition that frequency variation is from 6 kilohertz to 60 kilohertz. But there is a considerable noise at 120 hertz and 1 megahertz, and design a bandpass filter to reduce the noise by 90%. So you have to reduce noise at 120 hertz and 1 megahertz by 10%. So first you have to design a high pass filter. So we design a high pass filter first. So HP filter. So you have V out by V in equals to F by Fc root over 1 plus F by Fc whole square. You have unwanted noise 120 hertz. So you want to allow noise, you don't want to allow below 120 hertz to pass through. So 120 hertz and above you want to pass through. And signal is at 6 kilohertz. Okay. So if you put 120 here, let's say F equals to 120, so you will end up getting, and you have basically 10%, so 10% is 0.1, so 0.1. So basically you will end up getting from this equation Fc equals to, and V out by V in equals to 0.1. So you'll get Fc equals to be equals to 1194 hertz. And you still get but if you want to use, if F equals to 6K, then still you have V out equals to 0.98 V in, which is still your actual signal is not going to be lost. So you have this. So you have suppress the 120 hertz and below noise. Now let's move for this is high pass filter. Now low pass filter. For LP filter, you have basically same, a little bit different equation. V out by V in equals to 1 over root over 1 plus F by Fc whole square. So your F noise is equals to 1 megahertz, and signal is equals to 60K. So again, if your V out by V in equals to 0.01, sorry, 0.1, then you will end up getting Fc equals to 0.1 megahertz, 0.1 megahertz. So, and you will have at F equals to 60 kilohertz, you will have basically V out by V in equals to 0.8. So you're losing a little bit of signal here, is less than 90%. So you're losing a little bit signal here. So it is 0.86. So then if you do a plot, you can see this one, same thing. So you're losing a signal 0.86, and this is 10%, and this is 10%, 120 is, and below is less than 10%, and here you have 98% and 6. So 6 to 60, you still have 98 to 86% signal. And 1 megahertz and above, you have 10%, 120 megahertz and above, less, you have 20%. So this is how we can say that we have designed a band pass filter. Okay, so these are the filter problems that can be asked in the exam. Signal manipulation. Typically, sometimes you want to linearize the signal. So in that case, you may have to go for non-linear element, you have to go for linearization of the signal. This is not typical, this is kind of atypical. I rarely use this type of method. So let's say if you have a logarithmic system, then you can add a diode on the loop, and you can have it linearized. Similarly, protection is very important. So manipulation is not that of use, but sometimes you may want to use it. But protection, filtering, uh, conversion is very, very important. In the protection, what you want to do is basically opto-isolator or Zener diode protection is very common in electronics. So let's say if you have certain high current on this side, so you will burn the diode, but still this system, which is more expensive microcontroller side, will still be remain safe. So this type of protection, opto-isolation protection is very important in the case of electronics. Okay, let's do a few maths related to, I think this is Wheatstone bridge, if I'm not mistaken. So you have a resistance thermistor, which varies the temperature from 0 to 50 degree. The output range of the voltage of the Wheatstone bridge is 0 to 1 volt, approximately linear input-output relationship. So this is the resistance change equation. It is in Kelvin value, and these are the values you need to use for your design of the resistance in the bridge and the supply voltage. So let's try to do these things. Okay, so this is the equation. So if you put this equation 0 to 50 degree, 273 means 0 degree. So you will get R to be this value. And if you do 273 plus 50 degree, then R to be this value. And del equals to del R. Del R is the difference between these two maximum change. So del R by R, which is 0.84. And you know V out output voltage is del by 4 times V in. Let's say we assume the V in to be del to be 5 millivolt, sorry, 0.84. Del equals to 0.84 by 4. And output voltage is 0 to 1. This is given 0 to 1. So max is 1. So output voltage. So if 0 means it is balanced circuit, no temperature change. So it will be 1 means maximum temperature change. So you will have V in to be 4.76, which may be 5 volt is good enough. So, and this RG would be 8979.18, and R2, R3, R4 should be same as RG. So this is how you design the Wheatstone bridge circuit for your sensor system. So this type of questions also can be asked. I think this is the last slide. Let me check.